Hello there, and welcome. Tonight, we're going to talk about something that might seem strange to think about: the end of everything. Not just the end of our planet, or our solar system, or even our galaxy. We're talking about the ultimate fate of the entire universe itself. Now, I know what you might be thinking. Why would anyone want to spend time contemplating the end of everything? But here's the thing: understanding how the universe might end actually tells us something profound about how it works right now. It reveals the fundamental forces and principles that shape reality itself. And perhaps surprisingly, there's something almost beautiful about piecing together this cosmic puzzle. The good news, if you can call it that, is that we have time. A lot of time. Whatever happens to the universe, it won't be tomorrow or next year, or even in the next several billion years. We're talking about timescales that are almost impossible to truly comprehend. But scientists have spent decades developing theories about what the ultimate fate of everything might look like, and tonight we're going to explore all the major possibilities. But before we begin, please take a moment to like and subscribe, but only if you enjoy what I'm doing here. Also, leave in the comments where you're tuning in from and what time it is there. It's great to see how these videos connect people from around the world. Now get comfortable, dim the lights, close your eyes if you'd like, let the city noise fade away. Let's journey through time to witness the final chapter of the cosmos. Before we dive into the various scenarios for the end of the universe, we need to understand a few key concepts that will come up again and again. Think of this as building the foundation before we construct the house. The first thing you need to know is that the universe is expanding. This isn't speculation or theory at this point. It's an observed fact that we've measured countless times since the 1920s. But what does expansion actually mean? Imagine baking a loaf of raisin bread. As the dough rises and expands, the raisins all move farther apart from each other. But here's the key point. No raisin is at the center of the expansion. From any raisin's perspective, all the other raisins are moving away from it. That's roughly how the universe works. Space itself is expanding, carrying galaxies apart like raisins in rising dough. Now you might wonder, if everything is expanding, does that mean the universe will just keep spreading out forever? Or could something cause it to stop? Or even reverse? That question leads us directly to one of the most important discoveries in modern cosmology. In the late 1990s, astronomers made an observation that shocked the scientific community. They were studying distant exploding stars called supernovae, trying to measure how fast the universe was expanding at different points in its history. They expected to find that the expansion was slowing down over time, pulled back by the gravity of all the matter in the universe. Instead, they found the opposite. The expansion of the universe wasn't slowing down at all. It was speeding up. This was like throwing a ball into the air and watching it accelerate upward instead of falling back down. It made no sense according to everything physicists thought they understood. Something had to be pushing the universe apart. Working against gravity, scientists gave this mysterious something a name: dark energy. Here's the unsettling part. We still don't really know what dark energy is. We can measure its effects and we can calculate that it makes up about 68% of all the energy in the universe. But its fundamental nature remains one of the biggest mysteries in physics. And the fate of the universe depends crucially on what dark energy actually is and how it behaves over time. There's another factor that plays into the universe's fate: its overall density. Imagine you're holding a ball and you throw it straight up into the air. What happens next depends on how fast you throw it. If you throw it gently, it goes up for a while, slows down, stops, and falls back into your hand. If you throw it harder, it goes higher before coming back. But if you could somehow throw it fast enough, faster than about 11 kilometers per second from Earth's surface, it would escape the planet's gravity entirely and never come back. That speed is called escape velocity. The universe faces a similar question, but in reverse. It's expanding outward, but gravity is pulling everything back together. Whether the universe will expand forever or eventually collapse depends on whether it has enough mass and energy to gravitationally pull itself back together, or whether the expansion will overcome gravity forever. Scientists call the boundary between these two outcomes the critical density. If the universe has exactly this critical density, it will expand forever, but the expansion will slow down, approaching zero speed as time goes on, without ever quite stopping. Evidence suggests our universe is remarkably close to this critical density, though the accelerating expansion, driven by dark energy, complicates the picture significantly. With these foundations in place, we can now explore the various ways scientists think the universe might end. Each scenario depends on different assumptions about the nature of dark energy, the amount of matter in the universe, and the fundamental laws of physics themselves. Let's start with what many cosmologists currently consider the most likely ending, the Big Freeze, sometimes called the heat death of the universe. This scenario is based on our current best understanding of how dark energy behaves. If dark energy remains constant, if it continues pushing the universe apart at an accelerating rate forever, then the universe will keep expanding indefinitely. And that expansion has profound consequences for everything in existence. Picture the universe 1 trillion years from now. The Milky Way galaxy and its nearest neighbour, Andromeda, will have long since merged into a single, giant galaxy. But beyond this local group of gravitationally bound galaxies, the rest of the universe will have receded so far away that it will be invisible. The expansion of space will have carried distant galaxies beyond any possible reach, moving away faster than the speed of light. Not because they're travelling through space that fast, but because space itself is expanding between us and them. As tens of trillions of years pass, stars will continue to be born, burn, and die. But eventually, the raw materials for making new stars will run out. The universe will use up its hydrogen and helium, converting them into heavier elements through nuclear fusion in stellar cores. And one by one, the last stars will flicker and go dark. What remains will be a cosmos populated by dead stellar remnants. White dwarfs, neutron stars, and black holes, drifting in an ever-expanding void. Any planet still in orbit will slowly spiral into these remnants or drift away into the darkness. But the story doesn't end there. Even these remnants won't last forever. Over timescales that make the current age of the universe seem like the blink of an eye, even the most stable matter begins to decay. Protons, the particles that make up the nuclei of atoms, might not be truly stable. Some theories in particle physics suggest that given enough time, perhaps 10 to the power of 34 years or longer, even protons will eventually decay into lighter particles and radiation. If this happens, then everything made of ordinary matter, from dead planets to white dwarf stars, will slowly dissolve into a thin soup of subatomic particles. But there's one thing that might outlast everything else: black holes. These regions of space-time where gravity is so strong that nothing can escape are among the most enduring objects in the universe. A black hole the mass of our Sun would take about 10 to the power of 67 years to evaporate through a process called Hawking radiation. Supermassive black holes would take even longer, perhaps 10 to the power of 100 years. Can you even imagine such a time span? We're talking about a number with 100 zeros after it. The current age of the universe is only about 14 billion years, or 1.4 times 10 to the power of 10 years. The time it would take for supermassive black holes to evaporate is incomprehensibly longer, and after that, after even the black holes have evaporated, the universe would be an unimaginably vast, cold and dark expanse of space, filled with nothing but a thin gas of photons and elementary particles, spreading ever farther apart as space continues to expand. the temperature everywhere would approach absolute zero. No structures would remain. No stars, no planets, no galaxies. Nothing capable of supporting complexity or life or thought. This is the ultimate heat death, a state of maximum entropy, where no useful energy remains and nothing can ever happen again. The universe wouldn't end in a dramatic explosion or collision, but in a slow fade to black, an eternal darkness spreading in all directions. It's a melancholy picture, perhaps, but it's also strangely peaceful. And remember, this would take so long that the entire history of life on Earth, of human civilization, of all our struggles and triumphs, would be less than the first fleeting instant in the vast story of cosmic time. But what if the universe doesn't expand forever? What if, instead, gravity eventually wins? The Big Crunch scenario imagines a universe where the expansion we observe today is temporary. In this model, the expansion would slow, stop, and then reverse, causing everything in the cosmos to collapse back together. For this to happen, a few things would need to be true. First, the universe would need to be dense enough that gravity could overcome the expansion. Second, dark energy would need to either not exist or be weaker than we currently measure it to be, or somehow change its behavior over time. Given what we know today, the Big Crunch seems unlikely. All our observations point to accelerating expansion, not deceleration. But science is about following the evidence, and if our understanding of dark energy is incomplete or mistaken, we can't rule out this possibility entirely. So what would a Big Crunch look like? For billions of years, nothing would seem unusual. Galaxies would continue their cosmic dance, stars would be born and die, and the universe would look much as it does today. But eventually, careful measurements would reveal that distant galaxies weren't just moving away from us, they were slowing down. Then perhaps hundreds of billions of years from now, those galaxies would stop their outward motion altogether. There would be a moment, cosmologically speaking, when the universe reached its maximum size, and then, slowly at first, everything would start falling back together. The collapse would be subtle at first. Galaxies that are currently racing apart would begin moving toward each other. Over millions and billions of years, the average distance between galaxies would shrink. The cosmic background radiation, that faint afterglow of the Big Bang that fills all of space, would start to get warmer. As the collapse continued and gained speed, the universe would essentially run the Big Bang in reverse. Galaxies would crash into each other with increasing frequency. Space itself would contract, pulling everything closer together. The temperature would rise as space compressed, not because something was heating the universe, but because the photons filling space would be blue-shifted and compressed as space contracted. In the final stages, the universe would become too hot for stars or planets, or any complex structures to exist. Matter would be broken down into its constituent particles. Eventually, even atoms themselves would be torn apart by the intense heat and pressure. What would happen at the very end? Would everything collapse into a single point, a reverse Big Bang? Would it create conditions similar to those at the beginning of the universe, perhaps giving birth to a new Big Bang and a new universe? This is one of the great unknowns. The physics that governs matter and energy breaks down under such extreme conditions, and we simply don't have a complete theory that can reliably predict what would happen. Some physicists have speculated about a cyclic universe, where Big Bangs and Big Crunches follow each other endlessly, each universe dying only to birth the next. It's an appealing idea, philosophically, but we have no evidence that this is how reality actually works, and plenty of theoretical reasons to think it might not be possible. Now we come to one of the more dramatic and disturbing endings, the Big Rip. This scenario explores what might happen if dark energy doesn't remain constant, but instead gets stronger over time. Remember, Dark energy is the mysterious force causing the expansion of the universe to accelerate. Right now, we observe that this acceleration is relatively gentle and constant. But what if that changes? What if dark energy is not a constant property of space, but something that increases in strength as the universe ages? If dark energy grows stronger over time, the expansion of the universe would accelerate faster and faster, and eventually that acceleration would become so extreme that it would tear apart everything in existence. Let's walk through what this would look like, starting from a time perhaps 20 billion years from now. At first, the increased acceleration would be noticeable only on the largest scales. Distant galaxy clusters would disappear from view faster than expected as the expansion of space carried them beyond the cosmic horizon. But locally, within our own region of space, everything would seem normal. But as dark energy continued to strengthen, its effects would begin operating on smaller scales. Galaxy clusters would be the first to feel the strain. The space between galaxies in a cluster would expand so rapidly that gravity could no longer hold them together. Clusters would dissolve, their member galaxies flying apart. Then individual galaxies would begin to come apart. The space between stars would expand faster than gravity could hold the galaxy together. Stars would be flung into intergalactic space, orphaned from their galactic homes. You might think stars themselves would be safe, held together by their own gravity. But if dark energy kept growing stronger, even gravity on stellar scales would be overcome. The space between a star and its planets would expand catastrophically. Planets would be ripped away from their orbits and flung into the void. Then the planets themselves would disintegrate. The space between different parts of a planet would expand faster than the chemical and gravitational forces holding the planet together. A world would literally tear itself apart, and it wouldn't stop there. As the expansion accelerated even more, the space between molecules would begin expanding. Then atoms would be torn apart, their electrons ripped away from their nuclei, even atomic nuclei themselves. The protons and neutrons at the heart of every atom would be shredded by the expanding space between their constituent quarks. In the final moment, perhaps only a fraction of a second long, even the fabric of space-time itself might be torn apart. This would truly be the end of everything. Not just matter and energy, but space and time themselves, ripped to pieces by runaway expansion. The time until a big rip would depend on how quickly dark energy strengthens. Some models suggest it could happen in as little as 22 billion years from now. Others push it much farther into the future. And of course, this entire scenario depends on dark energy actually behaving this way, which current evidence doesn't strongly support. But the Big Rip represents an important possibility. It reminds us that the universe doesn't necessarily end quietly. If the fundamental forces shaping reality change in ways we don't yet understand, the ending could be violent and absolute. Scenario 4, the Big Bounce. Here's a more optimistic possibility. What if the universe doesn't really end at all, but transforms into something new? The Big Bounce scenario imagines that what we call the Big Bang wasn't actually the beginning of everything, but rather a transition point between a previous universe and our current one. And if that's true, then the end of our universe might not be an ending at all, but rather another transition to a new cosmic era. This idea has roots in quantum physics and attempts to understand what happens when you apply quantum mechanics to the universe as a whole. In classical physics, if you run time backward from the Big Bang, you reach a point of infinite density and temperature called a singularity. But singularities are signs that your theory has broken down. They suggest you're missing something important. Some physicists have proposed that quantum effects become important at extremely high densities before you reach a singularity. These quantum effects might create a kind of repulsive force that prevents matter from compressing to a mathematical point. Instead of collapsing to infinite density, a contracting universe would reach some maximum density and then bounce back, beginning a new phase of expansion. If this is true, our Big Bang could have been a big bounce from a previous universe, and the fate of our universe might be to collapse and bounce into yet another new universe, billions or trillions of years from now. What would this look like? In many ways, a universe heading toward a big bounce would resemble the Big Crunch scenario we discussed earlier. Expansion would slow, stop and reverse. Galaxies would fall back together. Space would contract and heat up. But instead of collapsing to a singularity, the universe would reach a state of maximum compression, where quantum effects dominate. At this point, the rules of physics would shift dramatically. The repulsive quantum forces would halt the collapse and reverse it, initiating a new expansion. What emerges on the other side of the bounce might be very different from what went in. The constants of nature, things like the strength of gravity or the mass of an electron, might have different values in the new universe. The laws of physics themselves might be subtly or radically different. This raises a fascinating question. If universes bounce eternally, how many have come before ours? Could there be an infinite chain of universes stretching back into the past, each one different from the last? And if so, what does that mean for concepts like the beginning of time or the origin of existence? These questions push at the boundaries of both physics and philosophy, and honestly, we don't have definitive answers. The Big Bounce remains a speculative idea, one possible way quantum gravity might work. We don't yet have experimental evidence for it, and the mathematics involved is complex and still being developed. But it represents an important alternative to scenarios where the universe simply ends. It suggests that endings might really be beginnings in disguise. Scenario 5, vacuum decay. Now let's consider something truly strange and somewhat unsettling. The possibility that the universe as we know it exists in an unstable state, like a ball balanced on top of a hill, and at any moment, without warning, it could roll down into a lower, more stable state, fundamentally changing the nature of reality itself. This is the vacuum decay scenario, sometimes called vacuum metastability. To understand it, we need to talk about something called the Higgs field. You may have heard of the Higgs boson, the particle discovered at the Large Hadron Collider in 2012. The Higgs boson is an excitation of the Higgs field, which permeates all of space. This field is responsible for giving mass to many fundamental particles. Without it, electrons and quarks would be massless, and atoms, chemistry, and life as we know it couldn't exist. The Higgs field has a property called its vacuum expectation value, which is basically the field's strength in empty space. This value determines the masses of particles and affects the fundamental constants of nature. Our universe exists in what's called a vacuum state, where the Higgs field has settled into what appears to be a stable configuration. But here's the problem. Calculations based on the standard model of particle physics suggest that our vacuum state might not be the most stable possible state. It might be what's called a false vacuum, stable for now, but not in the absolute lowest energy state possible. A true vacuum state with lower energy might exist, like a deeper valley in the energy landscape. If that's the case, then the Higgs field could theoretically undergo a quantum transition to this lower energy state. And if that happened, the consequences would be catastrophic. The transition would start at a random point somewhere in the universe. At this point, the Higgs field would suddenly shift to its true vacuum state. This would create a bubble of new vacuum, where the laws of physics are different. The masses of particles would change. The strength of fundamental forces might be different. In this new vacuum, atoms as we know them might not even be stable. The boundary of this bubble would expand outward at the speed of light, converting everything it touches from the old vacuum to the new one. You wouldn't see it coming, There would be no warning. One moment, you're going about your day. The next moment, the bubble wall passes through you, and the fundamental nature of matter changes. Inside the bubble, if atomic structures can't form or are unstable, all matter would simply disintegrate. Stars, planets, living things, everything would cease to exist in any recognizable form. The bubble would keep expanding, consuming galaxy after galaxy, until it had engulfed the entire observable universe. Now here's something important to understand. This is not an imminent threat. The calculations that suggest our vacuum might be metastable also indicate that if this is true, the probability of such a transition happening at any given time is extraordinarily small. The universe could exist in this state for an incomprehensibly long time, far longer than its current age, before a transition occurred, if it ever does at all. Moreover, there's significant uncertainty in these calculations. They depend on precise measurements of particle masses and other parameters, and small changes in those measurements can shift the conclusions. Some calculations suggest our vacuum is actually stable after all. We simply don't know for certain. But vacuum decay represents a particularly unsettling way for the universe to end because of its randomness and inevitability. If we live in a false vacuum, there's nothing anyone could do to prevent the eventual transition. And when it happens, it would be absolute and final, erasing not just life and structure, but the very possibility of their existence. It's worth noting that the fact we still exist and that the universe is 14 billion years old is actually evidence that vacuum decay, if possible at all, is extremely unlikely. The universe has had billions of years for such a transition to occur, and it hasn't. That suggests we're either in a truly stable vacuum or the metastability is so mild that transitions are vanishingly rare. The heat, death, revisited, entropy, and the arrow of time. Let's return to the Big Freeze scenario for a moment, but go deeper into what makes it such a profound ending. At its heart, this scenario is about entropy. Entropy is sometimes described as disorder, but that's not quite right. More accurately, it's a measure of how spread out energy is in a system, or the number of possible microscopic arrangements that would look the same at a macroscopic level. The second law of thermodynamics tells us that the total entropy of an isolated system always increases over time. Right now, the universe has lots of concentrated energy. Stars are hot, space is cold, matter is clumped into planets and galaxies rather than being evenly distributed. This represents a state of relatively low entropy. There are countless ways energy could be redistributed, countless processes that could still happen, but as time passes, stars burn their fuel. Hot things cool down, energy spreads out. The universe moves inexorably toward a state of maximum entropy, where energy is as evenly distributed as it can possibly be. In that far future, after all the stars have died and even the black holes have evaporated, the universe would be in a state called thermodynamic equilibrium. Temperature would be nearly uniform everywhere, just barely above absolute zero. No region of space would be significantly different from any other. And most importantly, without differences in temperature or energy concentration, no useful work can be done, no processes can run, nothing can happen. This is sometimes called the heat death of the universe, though it's really a cold death. It's the state of maximum entropy, where the arrow of time itself becomes meaningless. When nothing changes and nothing can change, does time even have meaning anymore? Here's a thought that might strike you as strange. We owe our existence to the fact that the universe currently has low entropy. The Big Bang started the universe in an incredibly low entropy state, with energy highly concentrated. The universe has been increasing in entropy ever since, and will continue to do so for trillions of years. But that increase in entropy isn't just destruction, it's what makes everything possible. Stars shine because energy flows from their hot cores to cooler surroundings. Life exists because organisms can extract energy from their environment and use it to build and maintain complex structures, increasing entropy elsewhere in the process. Thought itself depends on thermodynamic processes in your brain. In a maximum entropy universe, none of this would be possible. There would be no flow of energy, no gradients to drive processes, no way to sustain complexity or structure or life or consciousness. The universe wouldn't be hostile to life. It would simply be indifferent, lacking the basic conditions that make life possible. Does this mean the heat death is really the inevitable fate of the universe? Based on current evidence, it's the most likely scenario. But science is about remaining open to new evidence and new ideas. Our understanding of dark energy is still incomplete, and there could be surprises waiting as we probe deeper into the nature of reality. False vacuum decay versus bubble nucleation. A closer look. Earlier, we discussed vacuum decay as a potential end to the universe, but there's more nuance to this scenario that's worth exploring. The process by which a false vacuum transitions to a true vacuum involves something called bubble nucleation, and the physics behind it is both fascinating and strange. In quantum field theory, even empty space isn't really empty. It's filled with fields, and these fields can fluctuate randomly due to quantum uncertainty. Normally, these fluctuations are tiny and fleeting, but if our vacuum is metastable, there's a tiny probability that a quantum fluctuation could be large enough to cause a small region of space to transition to the true vacuum state. This would create a bubble of true vacuum surrounded by false vacuum. Whether this bubble grows or shrinks depends on its size and the energy difference between the two vacuum states. Small bubbles tend to collapse back to the false vacuum, but if a bubble nucleates above a certain critical size, it becomes energetically favourable for it to expand rather than contract. Once a supercritical bubble forms, it expands outward, driven by the energy difference between the two vacuums. The bubble wall moves outward, potentially accelerating to nearly the speed of light. Everything the wall encounters is converted from false vacuum to true vacuum, with all the attendant changes to the laws of physics and the stability of matter. What makes this particularly unnerving is its quantum nature. You can't predict when or where a bubble will nucleate. It's a purely random quantum event. The universe could exist in a false vacuum state for a googol years without incident, and then tomorrow, through sheer quantum chance, a bubble could appear and begin expanding toward us. But let me emphasize again, even if our vacuum is metastable, current calculations suggest the probability of such an event is so low that we shouldn't lose sleep over it. The expected time until a bubble nucleation event, if it's even possible, is likely far, far longer than the current age of the universe, possibly longer than any of the other end-of-universe timescales we've discussed. There's also a fascinating caveat. Some physicists have pointed out that the accelerating expansion of the universe might actually protect us from vacuum decay. If a bubble nucleated somewhere far away in the universe, the expansion of space could prevent it from ever reaching us. The space between us and the bubble could be expanding faster than the bubble wall is moving toward us, meaning we'd be forever safe from that particular bubble. The role of black holes in the far future. We've mentioned black holes several times, but they deserve special attention because they play such a unique role in the far future of the universe, regardless of which end scenario ultimately unfolds. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape from inside a boundary called the event horizon. They form when massive stars collapse at the end of their lives, or when enormous amounts of matter accumulate at the centers of galaxies. For a long time, physicists thought black holes were eternal. Once matter fell in, it was gone forever, and the black hole would exist indefinitely. Gradually, accumulating more matter over time. Then in the 1970s, Stephen Hawking made a remarkable discovery using quantum field theory. He showed that black holes aren't actually completely black. Due to quantum effects near the event horizon, they emit a very faint radiation, now called Hawking radiation. This radiation carries energy away from the black hole, causing it to very slowly lose mass. Given enough time, a black hole will completely evaporate, disappearing in a final burst of radiation. The time this takes depends on the mass of the black hole. A stellar mass black hole would take about 10 to the power of 67 years to evaporate. Supermassive black holes at the centers of galaxies could take 10 to the power of 100 years or longer. These timescales are so vast they're nearly incomprehensible. To put it in perspective, the universe is currently only about 10 to the power of 10 years old. The time until stellar mass black holes evaporate is longer than the current age of the universe by a factor of 10 to the power of 57. That's a trillion times longer. In a big freeze scenario, black holes would be among the last structures to exist. Long after all the stars have died, after all the protons have decayed, the universe would be populated by a sparse collection of evaporating black holes, slowly releasing their mass energy back into the cosmos as Hawking radiation. There's something poetic about this. Black holes spend most of their existence accumulating matter, growing larger, creating order out of disorder by concentrating mass into a tiny region. But eventually, quantum effects exact their toll, and the black hole pays back everything it took, radiating its mass back into the universe as disordered thermal energy. In the end, even the most powerful gravitational prisons succumb to entropy. But black holes might play another important role in some scenarios. In certain models of quantum gravity, the information that falls into a black hole isn't truly lost but is somehow preserved and eventually returned to the universe as the black hole evaporates. This is known as the black hole information paradox, and it's one of the deepest puzzles in theoretical physics, touching on the nature of quantum mechanics, gravity, and the fundamental structure of space-time itself. The resolution to this paradox might tell us something crucial about the nature of reality, and could even impact our understanding of how the universe ends. If black holes can somehow preserve and return information, they might play a role in cosmic cycles or in the possibility of structures or processes we haven't yet imagined existing in the far future. The Big Slurp, a variation on vacuum decay. There's a variation of the vacuum decay scenario worth mentioning, sometimes called the Big Slurp. This is similar to vacuum decay, but focuses specifically on the Higgs field and involves a slightly different mechanism. In this scenario, our universe exists in what physicists call a local minimum of the Higgs potential energy landscape. Think of it like a ball sitting in a small depression on a hillside. The ball is stable for now. It would take some energy to push it out of the depression. But there's a much deeper valley farther down the hill, representing a lower energy state. Through quantum tunneling, the Higgs field could potentially transition from our current state to this lower energy state. This transition wouldn't necessarily be instantaneous across the universe. Instead, it would begin at a point and expand outward, creating a bubble of the new vacuum that grows and eventually consumes everything. The term Big Slurp emphasizes the way this new vacuum would swallow up the old one, expanding at the speed of light and converting all of space to this new, lower energy configuration. What makes this particularly relevant is that the discovery of the Higgs boson in 2012 allowed physicists to make more precise calculations about the stability of our vacuum. The measured mass of the Higgs boson, combined with the known mass of the top quark, suggests we might be living in a metastable vacuum. However, these calculations involve significant uncertainties, and different analyses give different results. Some calculations suggest we're right on the boundary between stability and metastability. Others indicate that new physics beyond the Standard Model, which we haven't discovered yet, might stabilize the vacuum. The bottom line is that we're not certain whether this is a real threat or not, but even if our vacuum is metastable, remember that quantum tunneling to a lower energy state is an incredibly rare event, especially on the scale required to affect the entire universe. The expected lifetime of our vacuum, if it's metastable, could easily exceed 10 to the power of 100 years or more, far outlasting any of the other timescales we've discussed, except perhaps those in the most extreme Big Freeze scenarios, phantom energy and the Little Rip. Let's explore another variant of the Big Rip scenario, sometimes called the Little Rip or the Pseudo-Rip. This involves a particular model of dark energy called phantom energy. In the standard Big Rip scenario, dark energy increases in strength until it tears apart all structures, eventually ripping space and time themselves. The Little Rip is similar, but slightly less dramatic. In this model, dark energy grows stronger over time, but not quite strong enough to tear apart atoms or space-time itself. Instead, the Little Rip would still destroy all large-scale structures. Galaxies would be torn apart, stars would be disrupted, and planets would be pulled from their orbits. But atoms themselves would remain intact. The universe would become a vast expanse of isolated atoms, drifting in an ever-expanding void. Phantom energy models are characterized by having an equation of state, where the pressure is sufficiently negative that the energy density actually increases as the universe expands. This is unusual behavior. Normally, as the universe expands, energy density decreases because the same amount of energy is spread over a larger volume. Current observations of dark energy don't show this phantom behavior. The measurements we have are consistent with dark energy being a cosmological constant which doesn't change over time. But the uncertainties in these measurements are large enough that we can't completely rule out phantom energy models. If dark energy does turn out to be phantom energy, the fate of the universe would be somewhere between the Big Freeze and the Big Rip, depending on exactly how the energy density evolves. Structures would be destroyed, but the fundamental fabric of spacetime might survive, at least for some additional period of time. The ekpyrotic universe and cosmic collisions. Here's another intriguing possibility that comes from string theory and theories with extra dimensions. The ekpyrotic scenario. The name comes from the ancient Stoic idea of ekpyrosis, a cosmic fire that periodically destroys and renews the world. In the ekpyrotic model, our universe is a three-dimensional membrane, or brain, floating in a higher dimensional space. There are other brains in this higher dimensional space, and occasionally, two brains can collide. When they do, the collision releases enormous amounts of energy, which could appear to inhabitants of the brains as a Big Bang. In this picture, the Big Bang wasn't the beginning of time or the creation of space, but rather a collision between brains, and the fate of our universe might be to eventually collide with another brain, ending our current cosmic era and potentially beginning a new one. What would this look like? From our perspective, stuck on our three-dimensional brain, we couldn't directly see the other brain approaching. We might detect some unusual signals or forces as the brains drew close. Then, at the moment of collision, space would be flooded with energy as the kinetic energy of the collision converted to matter and radiation. The physics of what happens next depends on the details of the collision and the nature of the brains. Some models suggest this could lead to a cyclic universe, where collisions between brains occur periodically, each one giving rise to a new phase of expansion and cosmic evolution. Other models suggest that the collision could merge the two brains, creating a new, combined universe with potentially different properties and laws of physics. It's important to note that the ekpyrotic scenario is highly speculative. It's based on string theory, which is itself an unproven framework, and on the existence of extra dimensions beyond the 3 spatial dimensions we observe. We have no experimental evidence for any of this. But the ekpyrotic model is worth mentioning because it represents a completely different way of thinking about cosmic origins and endings. Instead of the universe being everything that exists, it's just one structure among many in a larger multiverse. And instead of endings being final, they could be transformations or transitions to new states. The conformal cyclic cosmology, death and rebirth of the universe. There's another fascinating cyclic model worth exploring, proposed by physicist Roger Penrose, called conformal cyclic cosmology, or CCC for short. This is a genuinely creative attempt to imagine how the universe might avoid a final ending by transitioning into a new beginning. Penrose's idea starts with the observation that in the far future of a big freeze scenario, after all, the black holes have evaporated and only massless particles, like photons, remain, the universe would lose any way to measure time or scale. Without massive particles, without structures that can serve as clocks, the concepts of time and distance become ambiguous. Here's where it gets interesting. Penrose suggests that this far future state of our universe, where everything has decayed into radiation, might be mathematically equivalent to the Big Bang state of a new universe. Both states are dominated by radiation, both lack any structure or scale, and both can be described by similar mathematics. In CCC, the universe doesn't truly end. Instead, the infinitely far future of one cosmic era becomes the Big Bang of the next. The universe cycles through infinite eons, each one beginning with a bang, expanding and evolving, eventually reaching a cold, sparse endpoint, which then transitions into the bang of the next eon. What's remarkable about this idea is that each eon could be vastly longer than the previous one, or shorter, and the transition between eons wouldn't involve any kind of physical collapse or crunch. It would be more like a mathematical transformation, a shift in perspective, where the endpoint of one era seamlessly becomes the starting point of the next. Penrose has even claimed to find hints of previous eons in the cosmic microwave background radiation, though these claims are controversial and not widely accepted by other cosmologists. The evidence he cites involves patterns in the CMB that could, potentially, be echoes or remnants from events in a previous eon. Whether CCC is correct or not remains to be seen. It makes specific predictions that can, in principle, be tested with observations of the cosmic microwave background and other cosmological data. But even if it turns out to be wrong, it represents an imaginative and mathematically sophisticated attempt to think beyond simple endings toward eternal transformation. The problem of quantum tunneling and stability. Let's dig a bit deeper into why the vacuum decay scenarios are so difficult to pin down and why physicists have such uncertainty about them. The core issue is that calculating the probability of quantum tunneling from a false vacuum to a true vacuum requires understanding physics at energy scales far beyond what we can reach in any particle accelerator. We can build theories and do calculations, but we can't directly test them. The calculations involve quantities called bounce solutions in quantum field theory, which describe how a bubble of true vacuum could nucleate and grow. These calculations are extremely sensitive to the precise values of various parameters in the standard model of particle physics, particularly the masses of the Higgs boson and the top quark. Small changes in these masses can shift the conclusions dramatically, moving the universe from definitely stable to possibly metastable to potentially unstable. Our current measurements of these masses are very good, but they're not perfect, and that residual uncertainty translates into significant uncertainty about vacuum stability. Moreover, the calculations assume that the standard model is the complete description of particle physics at all energy scales. But most physicists believe the Standard Model is incomplete. There are phenomena it doesn't explain, like dark matter, neutrino masses, and the matter-antimatter asymmetry of the universe. New physics beyond the Standard Model, whatever it turns out to be, could substantially affect vacuum stability. For example, if there are additional heavy particles we haven't discovered yet, they could stabilize the vacuum, making what appears to be a metastable state actually stable after all. Or they could do the opposite, making an apparently stable state metastable. This is why the vacuum decay scenario remains speculative. It's not that the physics is wrong or the calculations are bad. It's that we're extrapolating from what we know to energy scales and conditions we can't directly probe. And small uncertainties multiply into large question marks. The good news is that regardless of whether our vacuum is stable or metastable, if it is metastable, the timescales involved are so long that it makes no practical difference to anything in the foreseeable future. We're talking about expected lifetimes that could be 10 to the power of 100 years or more. For all practical purposes, we can treat the vacuum as stable. Dark energy, the greatest mystery. Throughout our discussion of how the universe might end, dark energy has played a central role. And yet, we still don't know what it actually is. Let's explore this mystery a bit more deeply. Dark energy was discovered through observations of distant supernovae in the late 1990s. Astronomers were trying to measure how much the expansion of the universe had slowed down since the Big Bang, expecting to find deceleration due to gravity. Instead, they found acceleration. Something was pushing the universe apart with ever-increasing speed. The simplest explanation for dark energy is that it's a property of space itself, what Einstein called the cosmological constant. In this view, every cubic meter of space has a certain intrinsic energy, and as space expands, more space is created, leading to more total dark energy and increasing acceleration. But there's a problem with this explanation, and it's one of the most severe problems in all of physics. When you try to calculate what the value of the cosmological constant should be based on quantum field theory, you get an answer that's wrong by a factor of about 10 to the power of 120. That's not a typo. The theoretical prediction is off by 120 orders of magnitude, arguably the worst prediction in the history of science. This enormous discrepancy is called the cosmological constant problem, and despite decades of effort, physicists haven't solved it. We don't understand why the observed value of dark energy is so incredibly small compared to theoretical expectations, nor do we understand why it has exactly the value it does. Because we don't understand dark energy, we can't be confident about how it will behave in the future. If it truly is a cosmological constant, it will remain steady, leading to a big freeze scenario, but it could be something more dynamic, a field that changes over time, which could lead to very different outcomes. Some models propose that dark energy is a field called quintessence, which can vary in strength and possibly even change from repulsive to attractive. If dark energy weakened over time, the universe's expansion could decelerate or even reverse, leading to a big crunch. If it strengthened, we could face a big rip or little rip. Other more exotic models suggest dark energy could even be a sign that our understanding of gravity itself is incomplete, that Einstein's general relativity breaks down on cosmological scales and needs to be replaced or modified. The truth is, we're still in the early stages of understanding dark energy. It's possible that observations over the next few decades will pin down its nature more precisely. New telescopes and surveys of distant galaxies should give us better measurements of how dark energy has behaved over the universe's history and whether it's changing. But it's also possible that dark energy will remain mysterious for much longer, requiring new theoretical insights or even entirely new physics to explain. Until we understand it better, there will always be some uncertainty about the ultimate fate of the universe. Could the laws of physics change? Here's a question that might seem strange at first. Are the laws of physics permanent and unchanging, or could they evolve over time? We typically assume that physical laws are universal and eternal. The same laws that govern atoms today governed them billions of years ago and will govern them billions of years in the future. But is this assumption justified? Some physicists have speculated that what we call the laws of physics might not be truly fundamental, but could instead emerge from deeper principles that we don't yet understand. If that's the case, then as the universe evolves into extreme states very different from what we observe today, the effective laws of physics could change. This is different from vacuum decay, where a transition to a new vacuum state changes the constants of nature but still operates within a consistent framework. I'm talking about the possibility that the framework itself could change. For example, in the extreme far future, when the universe is unimaginably cold and sparse, quantum effects that are negligible today might become important. The nature of time itself might change. Space might develop properties we can't currently conceive of. Or consider what happens inside black holes, or at the moment of the Big Bang. In these extreme conditions, our current theories break down. We know we need a theory of quantum gravity to describe them, but we don't have one. When we finally develop such a theory, we might discover that it predicts new phenomena or changes in physical law under extreme conditions. This uncertainty means that when we project the far future of the universe, we're really extrapolating our current understanding into regimes where it might not apply. The Big Freeze, Big Crunch, Big Rip, and other scenarios all assume that our current understanding of physics remains valid for trillions upon trillions of years into the future. That's probably a reasonable assumption. The laws of physics seem remarkably stable and consistent. But we should maintain some intellectual humility. The universe has surprised us before, revealing phenomena like dark energy that we didn't predict. It could surprise us again. The anthropic principle and why we see what we see. Before we continue, there's an important perspective to consider: the anthropic principle. This is the observation that the universe we see must be compatible with our existence as observers, because if it weren't, we wouldn't be here to see it. This might sound trivial, but it has profound implications for how we think about the universe's fate and the nature of the cosmos. Consider dark energy. Why does it have the value it does? One answer is that if dark energy were much stronger, it would have prevented galaxies and stars from forming in the early universe, and life would never have emerged. If it were much weaker or negative, the universe might have recollapsed long ago in a big crunch, again preventing life. The anthropic principle suggests that we shouldn't be surprised to find ourselves in a universe where dark energy has a life-compatible value, because only such universes can contain observers to measure it. This line of thinking becomes even more interesting if you consider the possibility of a multiverse, a vast collection of different universes, each with different values for the constants of nature, and possibly different laws of physics. In such a scenario, most universes might be lifeless, but life would naturally arise in those rare universes where conditions are right. And of course, all observers would find themselves in life-compatible universes. How does this relate to the end of the universe? Well, it suggests that we might be observing a universe during a particularly hospitable era, the time when stars shine, planets exist, and complex structures like life can arise and evolve. Both the past and the future are likely much less hospitable. Looking backward, the early universe was too hot and dense for complex structures. Looking forward, the far future will be too cold and sparse. We find ourselves in the middle, during the relatively brief cosmic era when life is possible. This doesn't tell us which end scenario is correct, but it does put our observations in perspective. We're sampling the universe during a special time, and our observations might not be representative of the universe's full history or its ultimate fate. The problem of very large numbers. Throughout this discussion, we've encountered numbers that are almost incomprehensibly large. Time spans of 10 to the power of 100 years, or 10 to the power of 1,000 years, or even longer. These numbers are so vast that they exceed our ability to truly grasp them. To put this in perspective, think about the difference between a million and a billion. A million seconds is about 11.5 days. A billion seconds is about 31.5 years. Already, the difference is hard to viscerally comprehend. Now consider that the current age of the universe is about 14 billion years, or roughly 10 to the power of 10 years. The time until stellar mass black holes evaporate is about 10 to the power of 67 years. The ratio between these numbers is 10 to the power of 57, a trillion, 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 trillion. What does such a span of time even mean? Imagine you could watch the entire current history of the universe, from Big Bang to today, in 1 second. To watch the life and death of a stellar mass black hole at that same rate would take longer than the current age of the universe by a factor of 10 to the power of 47. And yet, even these enormous numbers are dwarfed by the timescales involved in the decay of supermassive black holes, or the complete heat death of the universe. We're talking about numbers with 100 zeros or 1,000 zeros or more. Why do these numbers matter? Because they reveal something profound about the universe. The fact that such enormous timescales appear naturally in the equations governing cosmic evolution shows that the universe operates on scales vastly beyond human experience. Everything we know, all of human history, all of recorded time, the entire existence of life on Earth is less than the blink of an eye compared to the ultimate timescales of cosmic evolution. This can feel overwhelming or even nihilistic. If everything ends eventually, if even the atoms in our bodies will ultimately decay and the universe will expand into cold darkness or tear itself apart or undergo some other dramatic transformation, what's the point? But perhaps there's another way to look at it. The fact that we exist at all, that we can contemplate these vast timescales and understand something of the universe's ultimate fate, is itself remarkable. We are temporary patterns in the flow of matter and energy, conscious arrangements of atoms that can look out at the cosmos and see not just what is, but what was and what will be. Information and the end of everything. There's a deep question lurking in all these end-of-universe scenarios. What happens to information? In physics, information isn't just what's written in books or stored on computers. It's a fundamental property of physical systems, describing all the details about the exact state of every particle, every field, every quantum property in the universe. According to quantum mechanics, information is never truly destroyed. You can scramble it, spread it out, make it practically impossible to recover, but the information is always there in principle. This is called unitarity, and it's a cornerstone of quantum theory. But what happens to information in the end-of-universe scenarios we've discussed? In a big freeze, as black holes evaporate via Hawking radiation, it seems like information is destroyed. Hawking's original calculation suggested that the radiation coming from a black hole is purely thermal, random, and contains no information about what fell in. This contradicted unitarity and led to what's known as the black hole information paradox. Decades of work on this problem have led most physicists to believe that information is somehow preserved in Hawking radiation, encoded in subtle correlations between the emitted particles, but the exact mechanism remains controversial and is tied up with deep questions about quantum gravity. If information is preserved as black holes evaporate, then in principle all the information about everything that ever happened in the universe would eventually be released back into space as black holes evaporate in the far future. It would be hopelessly scrambled and impossible to reconstruct in practice, but it would exist. In a big crunch scenario, what happens to information as everything collapses? Does it survive in some form to seed a new universe? Or is it destroyed in the singularity? We don't know, because we don't have a theory that can describe the physics at such extreme densities. In a big rip scenario, where even atoms are torn apart, the question of information becomes even more vexing. If space-time itself is destroyed, can information survive? And in vacuum decay scenarios, when the universe transitions to a new vacuum state, with different laws of physics, information might be transformed in ways we can't predict. It might survive in some form, or it might be completely erased. These questions touch on the deepest issues in theoretical physics. They connect cosmology to quantum mechanics, to thermodynamics, to the nature of time and causality. And honestly, we don't have definitive answers. But the quest to answer them drives some of the most exciting research in physics today. Understanding what happens to information in extreme scenarios isn't just an abstract puzzle. It's directly tied to understanding the fundamental nature of reality. The multiverse and alternative endings. We focused on the fate of our universe, but what if our universe isn't alone? The idea of a multiverse, a vast collection of different universes, has gained traction in theoretical physics over recent decades, arising independently from several different lines of research. In inflationary cosmology, the theory that describes the very early universe, our Big Bang might be just one bubble in an eternally inflating multiverse. New bubbles constantly form, each one becoming a universe with its own Big Bang. Some versions of string theory also predict a vast landscape of possible universes with different physical properties. If the multiverse exists, then the end of our universe might not be the end of everything. Other universes would continue to exist and evolve, each with its own ultimate fate. In an eternally inflating multiverse, new universes would continue forming forever, even as old ones died. In this picture, there's no end to existence itself, only the end of individual universes within the larger multiverse. This raises fascinating questions. Could information or matter from a dying universe somehow transfer to a new one? Could travelers from a universe approaching its end escape into a younger universe? These questions veer into science fiction, but they're not entirely beyond the realm of physics. Some physicists have speculated about using wormholes or other exotic space-time structures to travel between universes, though we're far from knowing whether such things are possible. The multiverse concept also changes how we think about the anthropic principle. If there are countless universes with different properties, it's no surprise we find ourselves in one where conditions allow for life. And the end of our universe becomes less cosmically significant, just one event among many in a much larger multiverse. However, it's crucial to note that the multiverse remains speculative. We have no direct evidence that other universes exist, and it's not clear whether we ever could, since, by definition, other universes would be causally disconnected from ours. Some physicists argue the multiverse isn't really a scientific idea at all if it can't be tested. But even if the multiverse exists, it doesn't eliminate the question of endings. Even if our universe is just one among many, it will still end in one of the ways we've discussed, and the multiverse itself might have an ultimate fate depending on the nature of inflation and the structure of the larger reality it inhabits. Can intelligence survive the end? Here's a provocative question. Could intelligent life somehow survive or adapt to the end of the universe? This might sound absurd at first. After all, we've described scenarios where everything from atoms to space-time itself is destroyed. How could any form of intelligence persist? But some physicists and futurists have seriously considered this question. In a big freeze scenario, where the universe slowly expands and cools, but doesn't undergo catastrophic destruction, could advanced civilizations find ways to survive for extremely long periods? One scenario, explored by physicist Freeman Dyson, suggests that as the universe cools and energy becomes scarcer, intelligent beings could slow down their thinking processes to conserve energy. By thinking more and more slowly and going into long periods of hibernation, a civilization might be able to survive for an incredibly long time on the decreasing energy available. In Dyson's calculation, even in a universe approaching heat death, it might be possible for intelligence to persist indefinitely by carefully managing energy expenditure and taking advantage of quantum effects. Of course, this assumes a big freeze scenario and stable physical laws. In a big rip where space-time itself is torn apart, or in a vacuum decay event where the laws of physics change catastrophically, there's no plausible way for any form of intelligence to survive. There's also the question of whether it's meaningful to talk about survival when thinking might be slow to the point where subjective seconds are separated by eons of objective time. Would such an existence have any value? Would a being experiencing time so slowly even be conscious in any meaningful sense? These questions blend physics with philosophy, raising issues about the nature of consciousness, identity, and what it means to exist. They're probably not answerable with current scientific knowledge, but they're worth pondering. Another speculative idea is that advanced civilizations might find ways to influence the fundamental constants or structure of the universe itself, potentially staving off or altering the ultimate fate. This is purely in the realm of science fiction currently, as we have no idea whether such interventions are even theoretically possible. But it's worth noting that humans have come a long way in understanding the cosmos. A few centuries ago, we didn't know galaxies existed beyond our own. Now we can map the universe and predict its fate trillions of years hence. Who knows what capabilities a civilization millions or billions of years more advanced might develop? Still, there are likely hard limits imposed by the laws of physics. Some endings, like a big rip or vacuum decay, seem absolutely final, with no possibility of escape or adaptation. Intelligence, no matter how advanced, is still bound by the fundamental rules that govern reality. The search for answers. How we study the universe's fate. How do scientists actually study something as distant and uncertain as the end of the universe? After all, we can't observe it directly, and it won't happen for an incomprehensibly long time. The key is that the universe's ultimate fate is intimately connected to its current properties and behavior. By carefully measuring these properties, we can extrapolate forward and predict what will happen. One crucial tool is the observation of distant supernovae. These exploding stars serve as standard candles, objects whose intrinsic brightness we know. By measuring how bright they appear from Earth, we can calculate their distance, and by measuring how their light is stretched by the expansion of the universe, we can determine how fast they're moving away from us. By studying many supernovae at different distances, astronomers can map out how the expansion rate of the universe has changed over time. This is how we discovered that the expansion is accelerating and inferred the existence of dark energy. Another key tool is the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. This radiation contains incredible detail about the early universe, including its geometry, composition, and the seeds that grew into galaxies. By analysing tiny temperature variations in the CMB, cosmologists can determine properties like the total density of the universe and the relative amounts of ordinary matter, dark matter, and dark energy. Ground-based and space-based telescopes are constantly surveying large volumes of the universe, mapping the distribution of galaxies and measuring their properties. These surveys help us understand the large-scale structure of the cosmos and how it's evolving. Particle accelerators, like the Large Hadron Collider, help by probing the fundamental forces and particles that govern matter and energy. The discovery of the Higgs boson, for instance, was crucial for calculating whether our vacuum is stable or metastable. Computer simulations also play a vital role. Physicists can't build a universe in the lab, but they can create sophisticated computer models that simulate cosmic evolution, forward or backward, in time. These simulations help test theoretical ideas and make predictions that can be compared with observations. All these approaches involve uncertainties, of course. Measurements have error bars. Models make assumptions. There are aspects of physics we don't yet understand. That's why scientists continue to refine their observations and theories, gradually narrowing the range of possibilities. Over the next few decades, new telescopes and experiments will provide even better data. Projects like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope will survey huge swaths of the sky, finding millions of distant galaxies and supernovae. Gravitational wave observatories are opening entirely new ways to observe the universe, and experiments at the frontiers of particle physics continue to probe the fundamental building blocks of reality. Each new piece of data helps constrain the possibilities and brings us closer to understanding the universe's ultimate fate. We may never have absolute certainty. Science rarely does, but our understanding continues to improve. Time, meaning, and the end of everything. As we near the end of our journey through the possible ends of the universe, it's worth reflecting on what all this means, if anything. The universe, as far as we can tell, is indifferent to human concerns. It doesn't care whether we thrive or fail, whether we understand it or remain ignorant. The vast timescales and impersonal forces we've discussed operate entirely without regard to consciousness or purpose. This can seem bleak. Everything we build, everyone we love, every work of art and achievement of science, all of it will ultimately be erased by cosmic processes operating over unimaginable spans of time. From the perspective of eternity, nothing matters. But perhaps that's the wrong perspective to take. The universe may be temporary and ultimately doomed, but that doesn't negate the reality and significance of what happens within it. The fact that a symphony ends doesn't make the music meaningless while it plays. The fact that a book concludes doesn't make the story pointless while you read it. We exist in this particular cosmic moment, in this narrow window of time when stars shine and planets harbour life, and consciousness can emerge to contemplate existence. That's not diminished by knowledge of what comes before or after. There's also something profound about the mere fact that we can understand any of this. The universe has given rise to parts of itself, us, that can look back at the whole and comprehend its structure and fate. The cosmos has become self-aware through us, able to predict its own future and ponder its own nature. Perhaps meaning isn't something you find by looking at the entire span of existence from beginning to end. Perhaps meaning is something that exists locally, in the connections between conscious beings, in the experience of beauty and understanding, in the projects we undertake and the values we uphold, even if all of it is ultimately temporary. Different people will draw different conclusions from contemplating the universe's fate. Some find it humbling, putting human concerns in cosmic perspective. Others find it motivating, making the present moment seem all the more precious. Still others find it troubling or depressing. There's no single correct emotional response. The facts themselves, the expansion of the universe, the existence of dark energy, the ultimate dissipation or transformation of everything, are what they are, regardless of how we feel about them. The limits of knowledge. Before we conclude, it's important to acknowledge what we don't know and perhaps can't know. All our predictions about the universe's fate involve extrapolating current knowledge far beyond anything we can observe or test. We're assuming that the laws of physics as we understand them remain valid for trillions upon trillions of years into the future. That's probably a good assumption, but we can't be certain. There could be entirely new physics waiting to be discovered that would change everything. The history of science is full of surprises, phenomena that earlier generations didn't predict or couldn't have imagined. Dark energy itself is a recent discovery, one that dramatically altered our view of the universe's fate. Who's to say there won't be other surprises? There's also the question of whether the very distant future is even knowable in principle. Some interpretations of quantum mechanics suggest that the future isn't determined, that there's fundamental randomness built into reality. If that's true, then predicting the far future might be impossible, even with perfect knowledge of the present. And there are questions that physics simply can't answer. Why does the universe exist at all? Why does it have the laws and constants it does? What, if anything, came before the Big Bang, or exists beyond our cosmic horizon? These questions may be beyond the scope of science, requiring philosophy, or perhaps remaining forever unanswerable. Scientists try to be honest about these limitations. The best theories in physics make predictions that can be tested and are willing to be proven wrong. But when we extend these theories to the ultimate fate of everything, we're necessarily moving beyond what can be directly verified. That doesn't mean the exercise is worthless. Even if we can't be certain, it's valuable to explore the possibilities, to understand what our current knowledge implies, and to recognize where our understanding breaks down. The uncertainty itself is a kind of answer. It tells us about the limits of what we can know and points toward areas where new discoveries might be made. Closing thoughts. We've covered a lot of ground tonight, exploring multiple scenarios for how the universe might end. The big freeze where everything slowly dissipates into cold darkness. The big crunch where expansion reverses and everything collapses. The big rip where accelerating expansion tears apart all structures. The big bounce suggesting endings are really new beginnings. Vacuum decay, where reality itself suddenly transforms, and various other possibilities, each with its own timeline and characteristics. Based on current evidence, the big freeze seems most likely. The universe appears to be expanding at an accelerating rate, driven by dark energy that shows no signs of changing. If this continues, the ultimate fate is a cold, dark, increasingly sparse cosmos where no new structures form and existing ones slowly decay until nothing remains but the faintest traces of radiation in an endless void. But we can't be absolutely certain. Dark energy remains mysterious, and our understanding of physics at extreme scales is incomplete. The universe has surprised us before, and may surprise us again. What's remarkable is that we can have this conversation at all, that a species of primates on a small planet orbiting an ordinary star can look out at the cosmos and predict what will happen. Trillions of years hence is genuinely astonishing. We've come a long way from wondering if the stars were holes in a celestial sphere. The end of the universe, whatever form it ultimately takes, is unimaginably far in the future. No current threat, no near-term concern should be informed by scenarios operating on timescales of trillions or quadrillions or googles of years. The universe is young, and there's plenty of time for intelligence and life to flourish before any of these endings become relevant. What studying the universe's fate really does is help us understand the present. It reveals the fundamental forces and principles at work right now, shaping the galaxies and stars and planets we observe around us. It tells us about dark energy and the expansion of space, about black holes and thermodynamics, about the deep structure of physical law. And perhaps it puts things in perspective. Our lives are brief, our civilization young, our planet a tiny stage in a vast cosmic arena. But we're part of the story. We're here now, conscious and curious, trying to understand our place in the grand scheme of things. The universe will end eventually, in one way or another, but that ending is so distant, so removed from anything we need to worry about, that we can set it aside and focus on the present, on understanding the universe as it is now, on appreciating the beauty and complexity of existence, on making the most of the brief time we have in this remarkable cosmic moment. Will anyone be around to witness the end of the universe? Probably not, certainly not in any form we'd recognize. But even if the end is witnessed only by the universe itself, it's still worth understanding, still worth contemplating, because in doing so, we're exercising what may be the most remarkable ability conscious beings possess: the capacity to transcend our immediate circumstances, to look forward and backward across inconceivable spans of time, and to see ourselves as part of something much larger. The universe began roughly 14 billion years ago in an event we call the Big Bang. It will end, well, that depends on which scenario plays out, but the shortest timelines are measured in tens of billions of years, and most stretch incomprehensibly longer. Between that beginning and that ending, there's this: galaxies and stars and planets, matter and energy dancing through space and time, according to mathematical laws we can discover and understand. And for a brief cosmic instant, there's consciousness, looking out at it all in wonder. That's where we find ourselves tonight, not at the end, but in the middle, with enough understanding to glimpse what might come, and enough wonder to keep asking questions. Thank you for joining me on this journey through the possible fates of everything, whether the universe ends in fire or ice, with a bang or a whimper, in darkness or transformation. The story we're part of right now continues. And that's something worth paying attention to, for as long as we're here to see it.